Okay, start number 2. So now that we have done the evaluation, let's jump into the fray itself, the module. So this is our last module, okay, which coincidentally is the end of the semester, so it's a good thing we're done, right? So this is going to be our last module, module 10. It's going to be very short. We should be able to wrap it up this session. Maybe there's going to be a little bit of spillover to Monday session. But the goal here is that next week is your test-free week. So I made sure no deadlines were due next week. Actually, there was one that was due by mistake. I overlooked that, so I fixed this. So no deadline should be due next week. And as far as I'm concerned, I'm going to try to not introduce anything new next week. Okay, no new concept, no new technique, no new syntax, as much as possible, so that you have like this buffer between the end of the session today and the final exam, which is going to be on Saturday, Saturday 30th, noon 30 to 30, I think. You are going to have this buffer time to really deal with your other finals and review for this class. So we are going to have a reading assignment for this module as well, but this is like a one session module. So the reading assignment here is going to be a lot less strict, formal, whatever you want to call it, meaning that you should take a look at the chapter, do one superficial reading of it, okay? Just to have like the ideas that are going to supplement a little bit the lecture that we have right now, but that's about it. So it's not as in-depth as the other reading assignment we have done. In terms of learning activity, well, it's also a module that's on diet. So we have a practice exercise. These are going to be on a as needed basis. Okay. So it's a pick and choose. If you don't understand one of the concepts I'm going to explain today, then I really encourage you to do at least one exercise focused on that concept. Okay. If everything at the conceptual level is okay, then you should be already equipped for the final exam. I'm going to explain a little bit more how multiple dimension arrays are going to affect the final exam. And you're going to see that they affect it very, very, very insignificantly. PQ, yep, just to help you understand the reading. But again, this is not graded. So most of the stuff here is not graded. So it's a really relaxed module. Yeah. There is no over final. There is a final. I9 is not a final. Sorry. So I9 is the last dress rehearsal, if you want to look at it like that. Okay. So this is going to be the last IE that you have. It's going to be very similar in scope, length, difficulty, etc. to the final exam. So progressively, we have been ramping up, right? We have been getting closer and closer to the final. That's it now. So we have also a GE10. So this one is going to be graded, but it should not be taking a lot of time. And actually, if you are not able to complete it by the deadline, it's kind of like all of the other GEs is going to be flexible, okay? Meaning that before the semester ends, I will make sure that I review the logs for the server and integrate, the points for whoever completed something like that. So I'll send out an announcement probably before I do that for the last time, so that you have a chance to catch up on some points if you need to. The P's, they are the suggested one. Like I said, don't try to do all 6 of them. Just pick and choose 1, 2, maybe maximum if you have problem with the concept. The GE10 is going to be a little different. I was looking for something that would allow to make kind of like a review of the syntax, something that would throw in together everything that we covered during the semester. So what we are going to use is we're going to use another external software. So I gave you here the URL for this thing. You're going to have to enter the name of your instructor. Again, don't enter my email address. Enter kokcheng@usf.edu. And then you're going to be able to practice. So let me show you what that system is going to look like. Let me pull it up here. When you go to that URL, this is what you're going to get. Okay. Login page, write your email address here. Make up a password. Don't use a password that you use for anything serious. This doesn't have HTTPS enabled either. And then write your instructor email address here, kokcheng@usf.edu. Watch out, this is really picky. Okay, so let Google Chrome actually memorize your password. Okay, use a throwaway password that you don't care about. We're going to use this thing only one time. Okay, but it's really picky. Because when we developed this, actually, this is another like in-home product. When we developed this, we tried to go as far as we could to protect the student privacy, which means that the way that it's built, I'm not going to go in detail, but the way that it's built is your passphrase here, your email address, and the email address of your instructor, they all combine together to form an encryption key of sorts, okay? Meaning that if I wanted to know who did what on the server, I would have problem. But what I can do is send a list of your email addresses to that server, and the server will tell me if I know the email address and if you listed me as instructor, so in this case, Cockchain will do that for me, it's going to tell me how many exercises you completed so that I can give you a grade, okay? But everything else, even if somebody was breaking into the server or whatever, they could not see anything that anyone has been doing without the proper, keys and stuff like that. So that was just us like trying to experiment a little bit with student privacy. But once you log in, you are going to see an interface that looks like this. So let me get some stuff out of the way on my screen first. There we go. So you're going to see an interface that looks like this. It's going to be about solving problems, but you remember that little puzzle that we did at the end of one lecture? Well, that's the same thing, but this time the software manages for you. So it gives you an exercise. This is what the exercise is supposed to do. This is a solution to the exercise, except that it has been chunked into blocks, and the blocks need to be reordered. You reorder by drag and dropping like this, okay? And some of the blocks are duplicates, and if you look at the duplicates, the copy has generally an error. It could be anything, logical error, syntax error, missing semicolon, etc. So this thing is going to help you do several things. It's going to help you review a series of very classic exercise. If you are looking for extra practice, you can take the description of the requirement here at the top. You can try to work, forget the puzzle. I'm going to try to work out my own solution. So these are good roundup, exercise that are going to pull every bit of syntax we have been studying during the semester. If you are not quite ready for that, then you are going to see a solution and you are going to review your ability to organize the control flow of the program, but with some help. Okay, so you don't have to write from scratch. That's what the puzzle is supposed to do. And then spotting the duplicate fragments that are bugged, well, that's going to just give you a last training on syntactical issues, stuff like that, and your Where's Waldo skill all around, okay? Just right before the final. So everything that we covered during the semester is there, all the technique, tools, syntax, etc. So this is kind of a before the exam review. At any point, you can say, I give up on this problem. I really don't know how to solve it. And you get another problem that hopefully is not as long. And it's going to tell you here at the top how many you solved successfully. So if you submit, for example, I'm going to just do trashing this one. So the trash is here. I can untrash something by just dragging and dropping it, of course. But when I think that I'm ready, that I've reordered my program and trashed all the buggy parts, I submit, and it's not going to give you much feedback, but it's going to tell you, no, you're not there yet. So you try again, you review your code, etc. This is what's going to give you that last bit of practice before the final. Yeah, go ahead. Okay, say that again, sorry. No, you have to use the exact link that is in the slides. Okay, so I'm going to upload the slide. You have to use the exact link because it's down to the port number. Okay, there are many, many different versions of that software that are running on the server, not even talking about the EvoPy that we've used earlier in the semester. So if you just hit the server, you get something random. If you go to evoparson.cse.usf.edu, it's a very good question that you brought up. If you just go to that website, then you are going to get a copy of that software, but this is our sandbox, meaning that you can work, for like 10 hours on that and you're not going to get a bit of credit. So you really need to click the link that is in the slide down to the port number, okay? So practice a little bit with that. If you complete 10, you get full credit. You can complete less depending on whether that's useful to you or not, okay? And this will be lumped into your GE grade. All right, other than that, let's see if I can get my mouse back. Other than that, what we're going to talk about today is multi-dimensional arrays. So multidimensional arrays, that's the motivation right itself, right? This is, you want a matrix, you want a table, you want like something like that where you can store more than just vectors, or actually you can store multiple vectors in your matrix, right? So here's an example where we have a distance table and we have cities in the US. We have the number of miles that separate the city. This is a symmetric matrix, right? Triangular matrix. The middle here, we have just zeros. Distance of a city to itself is 0. This is just a particular example. How do we code this? Like this. That's actually the representation of that matrix. So it's a little bit different. Okay, we use curly braces. Well, we know about curly braces for initializing arrays, right? One-dimensional array. But here we use curly braces and then we specify multiple things also between curly braces separated by comma, and inside those curly braces, again, multiple elements separated by comma. So we are going to kind of dissect that. The structure is not that bad, actually. It looks weird the very first time you encounter it, but I'm going to show you that this is actually a very good representation of what's happening actually in memory. Okay, so if you are comfortable with that representation, then everything else is going to make sense. The learning objective for the module, again, I'm going to pass fast. Compared to the slides are going to cover most of it. There are just a few things that are left at the end of the slide as examples, if you need a further example or stuff like that. So let's talk about syntax. Declaring and initializing. This slide is very similar to the one about one-dimensional array. Okay, there is a good way, a good style to declare a two-dimensional matrix. There is a bad style to declare a two-dimensional matrix, depending on whether you put those pair of empty square bracket before or after the name of the variable. So that's the key of it all. Okay, instead of saying I want matrix to be, let's say, an array of int, only one pair of square bracket, you put 2. And now you read it, I want matrix to be a reference variable meant to hold a reference to an object of type array of int. And that's what a two-dimensional array is. Okay? It's an array of whatever value you want to store in there. So I really recommend that you adopt this notation here. That's going to be a good habit to take for the future. Of course, you can declare your reference variable, create the object. So then again, if you want to create an object which is a matrix of 10 by 10 int values, you create by uint square bracket 10. That's what we used to do for the one-dimensional vector. And then square bracket 10 again. That's it. We just double the square bracket notation. That's how we go to many dimension. Actually, we go to as many dimensions as we want. We could have a 3-dimensional, 4-dimensional, n-dimensional matrix there, okay? But you have to specify the size. For now, I'm going to tell you, if you build a matrix, you should specify both sizes. But I'm going to show you some code example where we're going to relax a little bit that constraint, and I'm going to show you that Java is capable to actually create a matrix where we know only the number of rows. And then the number of columns is going to change pretty much dynamically, kinda, okay? Asterisk, asterisk. So wait a little bit. In a few slides, I'm going to explain that thoroughly. But for now, if I want a matrix, I should know that I want a matrix 10 by 20, 5 by 3, and so on and so forth. So we are going to just roll with that for now. I can create the object right when I initialize and declare my reference variable, or I can declare the reference variable and then initialize the object, initialize it with a new object reference right here in several statements. And there can be some code between those two statements, of course. This variable here, I don't recommend that approach again. I recommend this one. This variable here, what's inside of it? Let's say it's a local variable in my main or in any function, in any method, sorry, that I'm writing. What value would I find inside matrix before I do matrix equal new int 1010? Okay, that makes sense. Null. Null would make sense. Unfortunately, and this is why I keep going back over this and I keep repeating it, right? Local variables inside method, you declare them, you don't initialize them, there's going to be garbage in them, literally. Okay, there's going to be whatever value the bits that just happen to be flipped to 1 and 0 in memory at that location indicate. So remember that, okay, because that's a source of bug, and that's going to come back to bite you sooner or later, even after you graduate, okay? It's if you don't initialize a variable, a local variable, you cannot tell what's inside. Does what I just say contradict other stuff I said? Kinda, but not really. I say kinda because at some point I told you, oh, Java is able to initialize those variable for you. But those variables were different. They were not local variable. They were attributes inside an object. Like for example, you create an array. Same question. What are the 100 values that are going to be in that matrix? I didn't set any value, but what can I tell about the value of those 100 elements? Now I can say something. I cannot tell for a local variable, but when I create an object, everything inside the object, if there are multiple int values or stuff like that, this is going to be initialized to 0. 0 for an int, 0.0 for a double, false for a boolean. There's a short list like that, okay? Or if it's a reference, like a string, no. So yes, don't get confused, okay? There is a default initialization behavior, but only inside object when you use the keyword new. And there is, most of the time when we declare local variable, no initialization by default at all, which can be a problem. Most of the time, the compiler will, however, be able to catch if you do something wrong and warn you. Okay, just be on the lookout for that kind of error. Accessing one element, it's the same syntax than arrays. Everywhere we were using a single pair of square bracket for the array notation, guess what? Now we use a double pair. So this is my number of the row, this is my number of the column, this is my coordinate X, my coordinate Y in the matrix, whatever you want to call them. Java doesn't care. Okay, Java doesn't care what does represent in your mind. It just knows that it has a table in memory, and you are going to address it by this index and that index. And then if you keep adding more dimension, then you keep following that logic. You keep adding empty square brackets when you declare, and then square brackets with a size when you create, and then square brackets with an index when you are trying to access. How do we iterate over the whole thing? And that's the main difference, okay? The syntax is not a big deal, but how are we going to consider iterate over every element? Look at them one by one. So with vectors, it's a linear operation. A vector is kind of a lineup of values, right? And you go, then you, then you, then you, then you, then you, then you. It's a loop. It's a for loop, right? Counter control for loop. We've done that, a lot of times lately. Okay. What about a matrix? So here's an example of a matrix. This classroom, right? We have rows of table, and then we have columns of seats, right? So if I wanted to hand over like an exam, what would I do? I would start here in the corner. Well, there's nobody there, nobody there, nobody there. You're my first victim. Here's your exam. Here's your exam. Nobody, nobody. Here's your exam. I reach the end of the row. That's kind of like what I did with one-dimensional arrays, right? It's just a counter control loop that go from the column number 0 to the column number whatever. But then what do I have to do? I have to repeat that job again for the second row. And I'm going back over, no one, no one, no one, here's your exam, no one, no one, no one, here's your exam, no one, no one, here's your exam. And then that was another loop. And then again and again and again. I'm not going to write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 loops. You crazy? I'm going to write one loop that says for every row in the classroom, and inside that loop, I'm going to write another loop that says inside that row that I'm looking at right now, for every seat inside the row, do something. Always nested counter control loops. When you deal with a two-dimensional matrix, you will have, if you want to look at every element in the matrix, you will have two nested counter control loops. If it's a three-dimensional matrix, you will have three nested counter control loops. The worst that people use in practice, I mean, gaming industry and stuff like that, is four-dimensional, okay? Four-dimensional matrices are used a lot for representing polygons and stuff like that in the gaming industry. Beyond that, you have to be doing some sort of scientific computation job, okay? It's really rare that we use 6, 7, 8, and 9th dimension matrix. But the logic is always the same. you have to iterate for every dimension of your matrix, all the rows, and inside the rows, all the columns, and so on and so forth. Okay? So here's an example here where we are iterating over the whole thing, and we are initializing every element inside the matrix to a random value. So for int row equals 0, row lesser than matrix.length row plus plus, I really recommend that you use names like row and col for column, okay? Because otherwise it can start looking really weird, okay? It's easy to get lost when you have like three-dimensional matrix even, and three different index like I, J, and K. You know, it's like which one is which after a while. This is going to allow you to always think, I'm going to access my matrix by first specifying the number of the row and then the number of the column. And for two-dimensional matrices, that makes sense. And that way you're not going to forget, you're not going to get confused. So the row is going from 0 to matrix.length. So that's weird. Matrix.length. If it was called matrix.size, I would expect, that a 10 by 10 matrix, the size is 100. But what is the length of a 10 by, let's say, 5 matrix? It's not 50. It's the length of the first dimension. So we are starting here to deal with, little peculiarities of the syntax. When you put the name of the reference variable that refers to a two-dimensional matrix and you use length to know its length, it's only going to tell you the length of the first dimension. If it's a 3, 4, 5-dimension matrix, same thing. Always dot length tells you the length of the first dimension only. So we have to deal with it. That's what Java does for us. That's it. The easy way to remember it is that it says length. It doesn't say size, right? So in this classroom, again, the matrix is rows per seat. So how many rows do I have? I have 10 rows. There we go. That's my length for this matrix. Second for loop, for int call equals 0, call lesser than, so it's still counter control loop. So if you are not used to counter control loop by now, this is your last chance to get used to them, applying them, to two-dimensional matrices. But generally, for most students at this point, you guys are comfortable doing a loop over an entire array. So we do it twice, and that's how we scale up to multiple dimensions. So int call equals 0, call lesser than matrix index I. Wait a minute, I thought a vector had one index and a matrix has two indexes. That's what I've been saying since the beginning here. Two indexes here, two sizes here, and so on and so forth. So yeah, but the Java syntax allows me to take the name of a reference variable that refers to a two-dimensional matrix, or even 3 or 4 or 5-dimensional matrix, doesn't matter, and only access the first dimension, or only access the first 2 dimension, or the first 3 dimension, or the first 4 dimension. So we can access all the dimension or access partially. And I'm going to explain to you exactly what the trick is here. But for now, consider that this means matrix index I, that means the row at index I. The first dimension represents the rows. The second dimension represents the columns in the matrix. So what I'm talking about here is, and this should not be I actually, I need to fix the slide. This should not be I, this should be row, okay? Sorry about that. So matrix at index row means I'm looking at the row number, row in the matrix, and I'm measuring its length. So if I look at the whole matrix and I measure its length, it tells me how many rows are there. If I look at one specific row, which is the notation to do so here in Java, and I look at the length, it's going to tell me how many columns are on that row. And this is going to generalize and scale up to whatever number of dimension. But for us, we are going to mostly stay put around 2, maximum 3 dimensions. How do I access the element? Matrix, index row, index call, equals, and then random number between 0 and 999. And then what we did with int, of course, we can do it with double. We can do it with any primitive data types. We can do it with strings. We have had arrays of strings. Well, we can have a matrix of strings, no problem. An n-dimensional matrix of string. So all of that stuff generalizes to n dimension. Again, for us, think 2 dimension, 3 dimension. I want you to be comfortable, somewhat comfortable with 2 dimension. Somewhat comfortable means you can read code, you can modify code, but you don't have to invent from scratch code that works on 2-dimensional matrices yet. Okay. So I want you to be at that level of comfort for the final. And then progressively, as you take more classes, they are going to maybe pursue a little bit in the higher dimension. That depends on how the class is structured. How do we declare, create, and initialize a 2-dimensional array? Well, we've seen an example already there before, right? So initialize to random number. Here's another example that instead of creating the array with a new keyword and then injecting values into it, using those 2 loops, what we're trying to do is we're trying to use that array block initialization syntax. Those curly braces that we use to represent a vector, right? And that meant create the array and populate all the elements in the array with those values. I want the same thing for a matrix. Well, the notation is a little weird. I say I want a 2-dimensional matrix of int. This is my reference variable. And then create a matrix and initialize it with those values. But the way that I write things, I'm going to have one complete vector here per row. So I use a block initialization syntax that I use for 1-dimensional array. So each row is a 1-dimensional array, right? Separate them by commas, and then say I want this many rows in my matrix. So each row is represented by a vector, like with the curly brace, and then I say the matrix is actually just a series of vectors, 1 per row, and that's it. So that introduces an interesting idea, the idea that a matrix, after all, is just one vector, and each element of that vector is itself a full vector. That's not exactly how we think about matrices, when we do math or stuff like that. We think of them like so, but we are going to see that in memory, they are represented a little differently. So going back to that slide, if I didn't use this notation, I could do things by hand, no problem. And as far as I'm concerned, for this class, you do it the way that you are comfortable doing it, okay? So here, declare the reference variable, first thing, then create the matrix of int of size 4 rows by 3 columns, and then populate the element at index 0, 0 is 1, the element at index 1, 0 is 4, and this should be the same values that there, right? They are even arranged 3 per line so that they match pretty much what is on the left. So whether you use this syntax or that syntax is entirely up to you. Of course, the syntax is a lot more verbose, a lot less readable. Some people could say that you are more likely to make a syntax error on the right than the left. So eventually you want to use the left-hand syntax, okay? But again, in this course, no rush. So I said that this is how we visualize matrices in our mind, right? Here's a matrix that is, the first one on the left is a matrix of size by 5 by 5. It's a table, no problem. So you told me that the first index would be the rows. So this is index 0, index 1, 2, 3, 4. Each of those correspond to a row. And then the columns, again, they're going to have indexes 0, 1, 2, 3, 4. Here's an example where I assign the element at index 2 for the row, index 1 for the column, the value 7. So here's my 5 by 5 matrix again, the same one. And this time I assign the value 7 right here. So addressing is very, very, how to say, familiar to anybody who has seen one-time matrix in the K-12 environment, okay? Or like in college or whatever. Or even if you play Battleship, well, you know already how to do that kind of addressing, right? This is the initialization with the block syntax that we talked about. So this time we have like a 4 by 3 matrix, nothing really transcendental there. The thing that is a little bit more interesting is that topic that I've been tiptoeing around until now, the dot length and the 1-dimension dot length syntax. So if I say matrix dot length here, we know the rule, okay? I gave you the rule without much explanation, but at least I gave you a practical, usable rule. Matrix.length, that means how many rows, how many elements in the first dimension of the matrix, to be really accurate. So 5, okay, no problem. If I say matrix index 0, So I'm not addressing one element of the matrix. It's two-dimensional. I specify only one dimension. That means I'm addressing an entire row, right? Matrix index 0, that's this row there. What is its length? Five columns in it, okay? So that makes sense. With those rules, that should make sense as well. Array.length, 1, 2, 3, 4. Yeah, the dimension of the length of the first dimension is 4. Array index 0.length, this is it, 1, 2, 3. So that's it. Okay, so we are able to measure the length of, measure the number of columns and the number of rows. The syntax is maybe just a little disturbing for some of you, depending on how okay you are with that kind of stuff. But really, the syntax can be fully explained. And that's the deal. When you understand how things are represented in memory, then syntax makes sense. Otherwise, if you don't understand this slide that I'm showing you right now, then you are stuck memorizing the previous slide and memorizing those arbitrary rules. So let's try to go a little deeper. Okay, why do we have to work out things this way in Java? Why do we have to write, x.length if x is a matrix, and then x index 0.length to get the number of columns? Well, when you declare a reference variable x, meant to be a reference to an object of type array of int, and then you create your object, what you get is an array of arrays of int. So the same way that I read the data type here, right to left, x is a reference to an array of int, okay? The same way I read that data type, it's exactly what it means in memory. So instead of that neat little table that we all picture in our mind when we think about the matrix X in this example, what you really have in memory is you have a reference variable X that stands alone. It contains a reference to an object. That first object is an array of 3 elements. That's the first dimension of your matrix. So that's why when I say x.length, it tells me 3, because X is just a one-dimensional vector. But what's the catch? What are the values contained inside that vector? Are they int, double, float? Are they reference to string? No. They are references to objects, 1, 2, and 3 objects. And each of those objects is also a one-dimensional array of, and this time, int value. So here's my matrix. X refers to a vector that contains a reference to each of the rows of the matrix. When I'm trying to access a specific element, I would say, for example, x index 1, and then that also index, for example, 3, and that's going to give me this element here. So that's why we're able to say x index 0.length. X index 0 is itself an array, it's a vector. The length of a vector is the number of elements in the vector, 1, 2, 3, 4 here. But I can also write x index 1.length. So here's x index 1 is here. This is a reference to a vector, a one-dimensional vector. Tell me the length of that vector, it's 4. And it's 4 for the last one as well. So I've been using x index 0 to get the number of columns of a matrix, but really I didn't have to. I could have used any of the row and say, tell me how many elements that row has. And it's going to tell me how many columns the matrix has. So creating, when I tell you, you create an object here, which is a matrix 3x4, that's another one of those things that we say all the time, but it's misleading. It's misleading when you're a beginner. If I tell you I create one object, which is a matrix object of size 3x4, you guys heard me. You create one object. Well, it's not accurate. The real story here is when you create like this, you create one object, which is pretty much the vector that points to each of the rows of the matrix. And then you create 1, 2, 3 objects again that are vectors. And these are going to each represent one of the rows of the matrix. Okay? So this organization in memory means that we have 4 objects actually in memory to represent a matrix that is 3x4 in size. So now the dot length should make a little bit more sense. Watch out about array index out of bound exception. If you try to access x index 3, boom, it explodes. If you try to access X index 0, index 4, it explodes. If you try to access X index -1, forget it. Negative index do not work in Java. What's next? Well, the next step is, so you tell me that the number of rows is the size of this array, and I can get the number of columns by looking at any row pretty much and checking its length. Sure, why not? But it looks like each row has its own length. So here's the next question. Can they be different? And the answer to that is yes, of course they can be. That's called a ragged array. It's an irregular sized array of arrays. So instead of having a perfect matrix, the syntax in Java, the way Java represents matrices in memory, allows us to do some funky stuff like this. So what am I doing here? I'm declaring a variable matrix reference to an array of int, and I initialize it. I say, okay, these are all the rows that I'm going to have in my two-dimensional matrix. The first row contains 1, 2, 3, 4, 5. The second row contains 2, 3, 4, 5. Then 3, 4, 5, 4, 5, and 5. So if I was querying, matrix.length, it tells me you have 1, 2, 3, 4, 5 rows in your matrix. That makes sense. Now, if I do matrix index 0.length, it's going to tell me inside that first row of the matrix, you have 5 columns. But if I do matrix 1.length, it's going to tell me in that specific row, you have only 4 columns. And yes, there is no obligation that all the rows in our matrix have the same size. Okay? So that allows us to do some neat stuff in Java, but that's a little, you have to stop the analogy with matrices here. You have to stop talking about, I'm using a matrix. You're not using a matrix. You're using an array where a one-dimensional array, where each element is itself a one-dimensional array. That's what you are using in Java. There's no such thing as matrix in Java. You could argue that point if you wanted. Okay, it's kind of a special case where all the rows have the same size. And what if I want a three-dimensional matrix? Well, I need a vector. That's going to say, for example, I have first dimension of the matrix is 2. So these are my 2 elements, okay? Each element here is going to refer to another vector. This is my first row. It has 4 elements. This is my second row. It has 4 elements. And then each of those elements is going to itself refer to a vector. So these 4 elements are going to refer to 4 vectors here that correspond to those tables. Those 4 elements to 4 vectors that correspond to the tables behind. It's always an array of arrays that contain, well, a value, if that's all you want, 2 dimension, or if you want more dimension, again, reference to more arrays that contain a value if you're done, or a reference to more arrays. And it can become a little, awkward to represent and to visualize, okay? So that's why we're going to mostly stick to 2 dimension in this course, maximum 3, because we don't need to go higher and make things artificially complicated. But that syntax and that representation of things in memory allow us to be very flexible in how we represent arrays of arrays and stuff like that, okay? For example, here's a reference variable called weird, an array of int. When I create it, now I do something weird. Well, okay, yeah, that's the point. What I do is I create an object, which is supposed to be a matrix. So you know that when I say create an object that is a matrix, that means creating multiple one-dimensional vectors. But I specified only the size of the first dimension. Can you do that? Can I actually not put any size? No. There has to be at least one size, the size of the first dimension. But can I skip the second dimension? Yes. Could I skip the third, fourth, fifth, etc.? Yes, all of them. The idea is that you can create actually this kind of incomplete matrix here, where you say, all I know about my matrix is it's going to have 5 rows. So Java knows that it needs to create an object, which is a one-dimensional array with 5 elements, and each element is going to refer to an entire, a series of elements, an entire arrays of elements. But for now, I don't know how many, so I just put a null in there, and I don't create those secondary arrays. So now I can have a loop and this is the weirdest part. Now I can say for every dimension, for every index in the first dimension of the matrix, weird index I, so there it is again. I know weird is two-dimensional, but now I use weird index I. What does that mean? That means the first row, right? So weird index I now, right now contains null. I want it to refer to a new one-dimensional array of size, whatever, I plus one. So what I did here is I said, I need a matrix with 5 rows. 1, 2, 3, 4, 5 elements, one-dimensional vector. And then I don't know yet how many columns are going to be in each row. So I put null in each of those guys instead of making them refer to another one-dimensional array. And after the fact, I realized, okay, now I'm ready to create those arrays that represent the second dimension. I iterate over every element, and I say, you are going to refer to an array of size. So I is going to be 0 to start off with. So 0 plus 1, 1. First element, you refer to an array of size 1. That's the first dimension. Second element, an array of size 2. Third element, an array of size 3, and so on, so forth. And then if I want to iterate, well, let's continue being weird, right? In this case here, I want to iterate over what? Every row. So again, the Java syntax notation allows me to say things like, for example, let's use a for each loop. For each element W of type array of int. So for each one-dimensional vector inside the matrix weird, how is that going to make sense? Well, again, the matrix weird is just a one-dimensional vector with, pointers to all of the rows, each of the rows. So for each row inside of the matrix weird, system.out.println arrays.toString weird. So W, sorry, that's the element that I'm using. So I'm displaying on the screen the rows of that matrix, element by element, row by row. And we can keep going like that, okay? So the connection to what we have been already studying and using is going to be simpler than that. What we just went over is arguably the most difficult point about multidimensional array, is that notion of, yeah, there's not really a matrix in memory, there is an array of arrays of arrays of arrays of arrays. Once you understand that, maybe it seems a little alien at the beginning, but if you work your way through it, you're going to make sense of it, and then everything is going to make sense, okay? But there is this initial little bump on the road that you need to get over. As far as the rest of the story about multidimensional array, can I use multidimensional array as parameter to a method? Yes, and you don't need to understand, at that fine level of details what's happening in memory. For example, here's the method sum. I want to be able to give to the method sum a two-dimensional matrix, and I want it to add up all the numbers together, return them to me. Public static int, that's the value that's going to be returned to me. Sum, int, square brackets, square brackets. My parameter m is, technically speaking, an array of arrays of int. My parameter m, I can visualize it more simply by saying it's a two-dimensional matrix of int value. How do I sum up all the values in the matrix? Total equals 0 to begin with. At the end, return whatever total is. And that part here, those 3 lines here, that should look familiar. That's how we iterate over every element of a two-dimensional array. So we are back to the beginning of the lecture. Okay, we kind of made a side trip here, like to learn exactly what's happening in memory. But right now, pragmatically, if I want to iterate over every element of the array, how do I do this? A counter control loop for each row, a counter control loop for each column. And you will note that here, I say that I start the column number at 0, and for each row, I look up the number of columns in that row, m index row dot length, so that if my matrix was a ragged matrix, every row didn't have the same size. Every time I'm about to sum all the elements in a given row, I check first the size of the row and I sum only that many elements. So for the first row, I could sum 4 elements. For the second row, 2 elements, then 1, then 5. It's going to adapt to the sizes of the data actually in your array of array data structure that you have in memory. And what do I do every time? I add this value to the running total, and that's pretty much it. And I get the sum of all the values that I passed. Okay. The rule is the same than with one-dimensional parameter. You pass a one-dimensional array to a method. The method can mess with the contents of the array. It's that whole passing by value, passing by reference thing that we keep discussing over and over, right? So you give a reference to an array, the method code can modify the value inside the array. If I give a reference to an array which contains arrays, does that change anything? No. I give the reference to an array. The method could modify, if it wanted, the values in that array, or explore the arrays that are linked from the first one and modify the value there. So in practical terms, that means what? If I give a reference to something more or less complicated that represents a matrix, then the code inside my method, if it wanted, it could actually change the values inside the matrix. So that makes sense, right? You give reference to one-dimensional array, the value can be changed. You give reference to an n-dimensional array, the values inside of it can still be changed. Okay, so this is at least consistent. Can we go beyond 2D? Yes, we can. Are we going to do that? No, not a lot. Definitely not a lot in this course, okay? But I just want to give you a heads up. Yes, you can go to whatever arbitrary number of dimension you need. For example, this would be an example of a data structure where I need 3 dimensions. I want to store some data about the performance of my students, okay? So I'm going to say I want a 3-dimensional matrix. The first dimension is going to be the ID of the student. So 0, 1, 2, 3, etc. The second dimension is going to be the ID of the exam. 0, 1, 2, 3, 4, 5, etc. Think about the IEs, for example, okay? And then the last one is going to be an index. I should not say ID, I should say index, really. So index of the student, index of the exam, and the last one is the grade that you received, for example, for that multiple choice or essay question, okay? So that's it. I have like a natural, 3-dimensional data structure. I didn't really wreck my head to find something complicated or something that is, sci-fi style or something like that. This is something that I could definitely use for a pragmatic problem, and it's already up to 3 dimensions. Well, if I wanted to say here, for example, this is going to be the index of the student, the index of the exam or the quiz. Let's talk about quiz. And then this is going to be the index of the question in the quiz. And then I add one more dimension that gives me the score that you obtain in that question or whatever, like which option you selected. I could keep going on and on and on like that, no problem. Okay. Yeah, sure, it becomes 4 or 5 dimensions, but the ID is always the same. As far as the syntax goes, well, you want 3 dimensions, but 3 square brackets. You want to initialize a 3-dimensional matrix. That's the logic behind the initialization block. 1 pair of curly braces. It all starts with a 1-dimensional vector. That's the first dimension. And inside that vector, I have references to a bunch of other vectors. These curly brace here, close this curly brace here. All of these are the vectors that are referenced to by the first dimension. What are they? They are like vectors of element. What are the elements inside those vectors? Vectors. So a 3-dimensional matrix is a vector that refers to multiple vectors. And inside of those vectors, each element is itself a vector. And inside that vector, each element is finally a double value. So a vector referencing vectors, referencing vectors, referencing doubles, containing doubles. Okay? All right. Typical task that we can do on those 2-dimensional arrays. So this is going to be just to put it in the slide so that you have easy access to it if you need to. But we've covered already all this. Can we initialize? Yes. This is a recipe. This is what you need to remember. If you want to assign a new value to any element of a matrix, for example, you read that value from the user, you use those 2 for each loop, one inside the other. If you want instead to assign a random number, like we did before, you use the exact same 2 for loops, and then you change what you do on each element of the matrix. Okay, so there are, again, for every topic, there are different level of understanding. The first level of understanding, even if you are panicking or whatever because of that, those remarks about the structure, don't. Get what you can. For example, these are practical recipes that you can apply like this just by using memorization. Memorize those things, apply them. As you apply them, scratch your head and try to make sense of what I explained before, ask questions, and then eventually you will have the full understanding. If I want to display all the elements of a 2D array or do any operation besides initialization on every element of a 2D array, again, these are the two for loop. Just like the for loop, for the one-dimensional array was always the same, pretty much. Well, these are always the same, except if I start doing fancy stuff like I want to skip one element over two in the first row. So for example, I want to go over only the even element in the first row. And then when I iterate to the next, I want to only consider the odd elements, odd index element. And then when I go back to the next row, I want to consider only, again, the even number element. Well, that would be an exercise in and by itself. Okay, that's not a bad thing for you if you want to try your hand at it, but it's going to be a lot more involved. But here, we're talking about just going over every element. Summing all the elements, again, that means going over every element, adding them to a total. We've seen that. This one here is actually better in the sense that it doesn't assume that you have non-ragged matrix. So the first one is a sum of all the elements, okay? This one is a little more peculiar. This one says, I want the sum of every element for the first column, display it. Then I want the sum of every element for the second column, display it, etc. While matrices in Java are really easy to iterate over, when you go row and then column, row first and then column. If you try to say, I want to iterate over the columns, it's not that trivial anymore, okay? So what we're doing here is we say, I need a for loop that says for column equals 0 to column lesser than matrix index 0 dot length. So I take the first row, as my measure of the number of columns for the whole matrix. That's why it assumes non-ragged to the array, okay? Because I only look at the length of matrix index 0, and I'm assuming that all the others are the same length. Otherwise, I would be in trouble. Total equals 0, so I want to sum all the value in the column. For each row equals 0, row lesser than matrix dot length. So now I use matrix dot length because there's no way for me to say just the length of that column. It's either I say matrix dot length, which gives me the number of rows, or I say matrix index, and one value here that specify one specific row, and it gives me the length of that specific row. But I cannot say, for example, let me jump immediately to column number 2 by using the square bracket notation. So here I'm going to iterate over row, going over those values, and add to the total matrix index row column. That part is the same. But see, the organization here is slightly different. And then at the end of all those loops, of that internal loop here at display, the sum for the column index of the column is whatever total I computed. And then I go back to the next column. Now column equal 1, total is reset to 0. And then again, we go through it. Shuffling, same thing. Not going to be a big difference from the previous version. I consider so we are back to trivial stuff, trivial, simpler stuff at least. I consider every element in my matrix, generate 2 random indexes. So now that I have 2 dimensions, I need 2 indexes, and then swap my current element with that randomly chosen element. And pretty much I'm doing this in my matrix, okay? I'm going like element by element, and for each element, I pick another random, replace them. Then go to the next one, pick another random, replace them. Go to the next one, etc., and do that for each row, for each column, okay? So this gives you like the analog to what we did with one-dimensional arrays. Now, we're almost at the end. So what you are going to find, I'm going to upload the full PDF, okay? But I need to make some time to give you a heads up on other stuff. So I'm going to stop here for this slideshow. You're going to find pretty much in the rest the stuff that was in gray in the learning objectives, so the stuff that is actually detailed also in the reading assignment. So just a few examples of programs, okay? Next week, we are going to do a fake exam, pretty much together. during the two sessions, and I'm going to use the session for Q&A as well. So when we do that, I'll show you exactly how 2D arrays are going to be used in the final exam. And you are going to see that the intent is really to use only a fraction of everything that I covered today. So if you understand pretty much the gist of what I covered today, and you do those reading assignments to look at the example, then you are more than ready for the final exam. The last thing I want to show you is I'm going to open another module. And in that module, you're going to find a slideshow, yet another slideshow. This is the last one, I promise you. And this slideshow is going to give you details about the logistic of the final exam. Since I generated the PDF for that, I had a line here that says the room has not been assigned yet. I just got an email last evening or something like that. This is the room for our exam. So all of the rules for the final exam are in the slides. I'm going to go over them Monday, but I want you to have them already so that you can take a look and you can, ask questions on Piazza, stuff like that over the weekend. The bottom line is the sooner you have that information, the better for everybody. So I'll go over it Monday, don't worry. I'll answer your question, but here are all the details for the exam, including where it's going to be held, when it's going to be held, and it's definitely in person, face-to-face. So let me be clear about this. If somebody somehow logs in, take their final exam from home, that you just got a 0 and 40% of your grade. Okay, I cannot work around that level of, I'm disconnected with the announcement and I'm disconnected with the slide and I'm disconnected with whatever the guy is saying, in the video that I recorded. You need to pay attention. Final exams are not a joke. The detail of the logistics are all important. If you mess that up, yes, you can fail your class just because you misunderstood or misread a slide. That can definitely happen. It has happened in the past. I don't want it to happen. Okay, so be careful. So you are going to find some examples, some details, exhaustive details about the exam. You are going to find a mock exam helper.java. This is just to show you the two file format, but I already covered that. So this is not a fake exam in the sense of showing you the kind of question. This is just to show you the format of the exam with the method, spilling over in two different files. We are going to look at that in detail again Monday, don't worry. And then after that, you are going to get 1, 2, 3 fake exams. So these are previous exams. They are not the full exams, actually. They are just one question, the question that I thought was the best for you to practice and train with, okay? So these are like 3 different exams, 2017, 18, and 19. And we are going to pick one question in each of those exams. I'm going to upload the files. They're going to be there. You can download the file. They're going to look exactly like the file that I gave to the student for that question as exam. And you can use those to put yourself in the condition of the final exam. Next week, we are going to work on those. I'm going to add one more next week that we are going to do in class, which is going to be the one from last year, 2020. Okay? So pretty much you'll have a total of 4 previous exams to be exposed to get a good idea, get comfortable with the level of difficulty. And if you realize that you are overwhelmed, you have over a week. That's your last chance to catch up. Okay, as the TAs and I, we are there to help you. So come and see us, let's do the best we can. Like one of my colleagues says to his student, I guarantee you that if you come to office hours, we can get you a little more comfortable than when you came in with whatever topic, no matter how back, you're stuck, etc. But the only thing that I cannot guarantee you is that in that 1 week, I can grab anybody who is like stuck at Hello World and make them ready for the finals. But I will guarantee you progress, okay? All right, thank you for your attention, and that's the last lecture.